Okay, we're going to work ahead and develop the concept of the Bernoulli equation, which is what I had mentioned in class, really is just another form of the energy equation. In this case, a mechanical energy with the pressure term. So here's our streamline, and let's consider a point on the streamline. We'll say that that's right there. We call that point 0. And what we'd like to do is consider a small volume, some delta volume, around that point. And we're going to take a look at all the forces that are acting on it. All right, so let's be a little bit more formal here. And what we'll do is let's create a box that would stand for our volume. And at the center of that box, we'll put a point, and we're going to call that point, or the pressure at that point, P0. Now our box, in the streamwise coordinate, we're going to say it has a distance of delta S. Now there's going to be an area on either side of the box, so let's kind of draw the little box over here. We'll keep that with the green pen. And the side of the box is going to be a delta X into the paper and a delta N, what we're going to call a normal direction. So this would be the direction normal to the streamline, and the direction X is going to be, I guess, perpendicular to the streamline, if you want to call it like that. All right, so these two are basically, so the sum of delta X and delta N, or the product rather, are going to create a delta area, so some small area. Now, acting on these surfaces, by the way, we're just going to be looking at the pressure term now. We'll come back and pick up the gravity term in a second video. So what we got going on here is we have P naught, and the thing is P naught is at the center, so this is going to be minus some value of delta P, because we're going to impose a positive direction. So this is the positive streamwise direction. And on the other side of this, we're going to have P naught plus delta P. So what we're basically saying is that as we move from this side to this side of my differential volume, that we can say pressure is going to either increase or decrease. So pressure will change, or at least we're leaving the possibility for the pressure to change. All right, so what is that going to give us? Well, if we work under the assumption that Newton's law is going to hold, we're going to find out that the sum of the forces will equal mass times acceleration, correct? Well, the mass that we're working with is going to be the mass that's inside the inside that box. So this is going to be, instead of m, it's going to be delta m, and the acceleration that we're looking at is the acceleration along the streamline. So we're going to say that it's just not a, it's going to be as, and likewise we can impose a direction on our force term, and these are the forces that are acting on the s direction. So keeping it here, we're going to find out that delta m is going to be equal to a density of the fluid, and we're going to consider a constant density fluid, which is going to be one of the requirements of the Bernoulli equation, and this is going to be multiplied by delta volume. So if this is delta area, and we have delta S, we're going to actually find out that the delta volume term is going to be delta S times delta normal and times delta x. And while we're here, why don't we keep talking about the acceleration term? So AS, well, it's just the derivative of the velocity, right? So we have fluid moving along the streamwise coordinate. So this is the velocity in the s direction. But if we do that, as we learned in dynamics, we can utilize the chain rule to say it's dvs ds times ds dt. And if we take the time derivative of our motion along the s direction, well, that is just vs. So we find out that our acceleration term as is vs times dvs ds. Alright, so we put all this together, and what do we find out? We find out that the sum of the forces in the streamwise direction is going to equal rho times delta volume times Vs. You know what? Let me write this down lower. Yeah, I can squeeze in a little bit. I can. All right. So I'll actually even change the color because this is important. So we're going to say that the sum of the forces in the streamwise direction is going to equal the density of the fluid times the volume. So I'm actually going to write all three terms here: delta S, delta N, and delta X, times the acceleration of the fluid along the streamwise direction. Now notice that because it's written this way, we still are able to say that we have steady flow, because the acceleration in this case is only due to the fact that the flow moves, or that the fluid is moving in the S direction. We'll come back to that and pick up that discussion in a little bit. So it's going to be times Vs, the velocity along the streamline, and times the derivative of that with respect to motion along the streamline. All right, so that's one expression for the sum of the forces in the streamwise direction. Well, so this is the MA term, but we want to figure out where the forces are. So if I go back up here and we take a look at our box, we're going to want to add up these forces over here. Well, let me throw it over here. We know that a force, when we're dealing with pressure, is going to be P times the area. So what we're going to do is take all these forces, these pressures, and multiply them by their respective areas. So I'm going to come down here and I'm going to draw our box again so we have something to kind of take a look at. Get back to my blue pen here. And, didn't get my box, but that's okay. So on this side, we have a force acting, and I have this side as a force acting. So this is going to be in the positive direction, and this is the negative direction. So if I sum the forces, the sum of the forces in the x direction are going to equal P naught minus delta P times the area, which is going to be delta N, delta X, and we're going to subtract from that P plus delta P naught. Actually, it's P naught plus delta P, again times delta N, delta X. All right, and we need to equate these two. So we have two expressions for the force. Well, the one term that we really don't have a handle on right now is this delta P term. All right, we have rho. We kind of know what delta S, delta N, delta X are. That's our volume. And Vs, dVs, ds is a term that we're familiar with. We kind of understand what's going on with it. So what is going on with delta P? Well, let's take a quick look. The book will always refer to something as being the first term of a Taylor series expansion, which is true, but it's always kind of a mystery. So let's take a look if we figure out what's going on here. So if this is the pressure coordinate, and we plot the pressure as it varies as a function along the streamline, let's just draw some random curve here. And let's come up from some location on our streamline to our curve, and we'll come over here and we'll call that term P naught. Now if I go some distance behind S and some distance in front of S, what are we doing here? Well, we're doing this. We're going some distance in this direction and some distance in this direction. So we'll make them even, and we'll say that they're both delta S over 2. So this total distance here is delta S, and this distance is delta S over 2, and this distance is delta S over 2. So if I come up, this is 1 minus, so this point here, and we can bring over, and we have this point here. Make these green. So this one is P naught minus delta P, and this one up here is P naught plus delta P. Okay, but now what we're trying to do is figure out how to relate those. So the whole deal about the first term of a Taylor series expansion is, of course, that if you remember from calculus, I can utilize the derivatives of a function to describe the function itself. Well, the first term that we'd end up with is just the straight line, which is defined as the derivative dp ds. But of course, if we're talking about differentials, right, the Taylor series can be utilized to describe the entire function. We don't really want to describe the entire function. We're just looking for this little volume area of it. So what we can do is say that this line, which is given by dpds, is sort of good enough for us. That's what they mean by just using the first term of the Taylor series expansion. So anyway, still, what is this getting us? Or what does this have to do about the price of tea in China? Well, we do remember something from our high school algebra. If this is y, and this is x, and this is b, then we can call a straight line where we have the slope m, right? Y equals mx plus b. Well, in this case, we are looking at this side of the plot, so this point becomes P naught. The slope becomes dp ds, and the x term that we're dealing with, we're trying to find out where y would be. All right, so this is P naught. M is dp ds, and what we're looking for is y is going to equal P naught plus delta P. So what is the x term? Well, the x term, if this was 0, this entire location would be delta S over 2. So what we find that is P naught plus delta P is dp ds times delta s over 2 plus p naught. Very exciting. All right, so we're going to take that and we're going to substitute it in here. So let me rewrite them again. So we find out that p naught plus delta p is going to be equal to p naught plus dp ds times delta s over 2. So that's the first term. And p naught minus delta p is going to be equal to p naught minus dp ds delta s over 2. All right, apologize for this getting a little sloppy, but we'll come back and we'll take all the terms over again. All right, so this is what we're trying to do. So let's put our terms in. Change the color again so we can see what we're doing. All right, so sum of the forces in the s direction is going to equal, well, p naught minus delta p is going to be p naught minus dp ds delta s over 2, and all of that. Well, let me take these last two things away, because we see that up here delta n, delta x is multiplied by both of those. So I'm just going to put a bracket around these, and now we're going to go minus the p naught plus delta p term, which is this one up here. So it's going to be minus p naught plus dp ds delta s over 2. And we'll close the square brackets and we'll add in the term delta n delta x. Well, if we take a look here, we see that we can propagate out a delta s from both and bring them out this side, and we're going to see that p naught minus p naught are going to cancel. So this term is going to cancel, my delta s is going to come out, and now I'm going to have a minus dpds minus a plus dpds, and they're both a half. So what we end up with, you might want to do the math yourself on a sheet of paper, is we have minus dp ds times delta s delta n delta x. That's very sloppy. So let's try that again. Let me get a better pen. I'll write this in blue and a little bit thicker. So we find out that the sum of the forces in the s direction are equal to minus dp ds times delta s delta n delta x. So that's the forces, and this also has to be equal to the mass times the acceleration, which was rho times delta s delta n delta x times vs dvs ds. So now we want to equate these two terms, and we can see, hopefully, that the volume term is showing up on both sides. So before I even rewrite them, we're going to turn out that we can actually cancel the volume terms. So what we're going to end up with, go back to my blue pen, is that we have minus dp ds equals rho times vs dvs ds. Now, we'll talk about this more, but as we've seen in dynamics, that when we have an expression like this, we can treat the differentials as algebraic terms, which means I can cancel the ds on either side. And what this leaves us with, and I'm going to divide through by rho, so I'm going to have minus 1 over rho dp equals vs ds. And again, you're still wondering where the heck it is that we're going, but we're almost there, because what we can do now is we can integrate both sides. Well, the integral of dp is of course just p, so we end up with minus p over rho, but since this is an indefinite integral, we didn't have any limits on it, we'll say there's a c1 over here. And on this side, well, the integral of vs ds, well, you might not recognize that, but you certainly recognize x dx as equaling 1/2 x squared. So this is just 1/2 vs squared, and again there's another constant here, we'll call that c2. So the last step, and we're staring at the Bernoulli equation, we just have to rewrite it in a term that looks better for us. So I'm going to bring this term over here, and I'm going to combine my constants over there, and rewriting it, we're going to end up with p over rho plus vs squared over 2 is equal to a constant. And there you go. There's the Bernoulli equation without gravity. So we'll add that term in a second. But what is it telling us? Well, it's saying that if we have a streamline and fluid is moving in a steady fashion across the streamline, what do I mean by steady? Remember we said that there was a valve here? I can have the valve being turned on and off. Well, as long as there's a constant flow rate of fluid coming through here, the flow is considered steady. Now, if I had someone opening this valve, then the flow would be unsteady. But as long as the valve is not being changed, we would have flow passing a point 1 and flow passing point 2. And we'll be talking about something called the continuity equation, but the mass flow rate passing this point has to equal the mass flow rate passing that point. So we have conservation of energy and conservation of mass in this equation. And so what we're going to do is we're going to say that P1, the pressure at point 1, divided by the density, will equal the V1 squared. I'm going to drop the S term in terms of that we're now imposing the fact that it's along a streamline, is going to have to equal to the pressure at 2 over rho plus V2 squared over 2. So this is sometimes the more often expressed version of the Bernoulli equation. So I'm going to call it that. Just recognizing that there is another term in here for the hydrostatic pressure or the hydrostatic energy term. So we'll call this the Bernoulli equation with a star next to it, because we know we have to add our term in. So this is basically telling us that the pressure in the fluid and the kinetic energy in the fluid are intimately related to each other. If the pressure goes down, the velocity is going to go up, and if the velocity goes up, the pressure has to go down. And there's a lot of magic that goes on with this. Now, of course, remember that when we drew our little box over here and we imposed the fact that there was pressure here and pressure here not being equal to each other, we also did not take into account in the streamwise direction that there would be a shear stress acting all the way along this. So if there's no shear stress under consideration, that's one of our requirements for the Bernoulli equation. So tau equals 0. So in viscid flow, we also said that the flow has to be steady along the streamline. We're utilizing this form of acceleration. So this is referred to as convective acceleration. We'll come back to that term again at later points. But that means that we have to have the ddt terms equal 0. So steady. I didn't say it explicitly, but when we did this integration over here, we took rho out as a constant. So rho equals a constant, another term. So rho equals a constant. So that means it's incompressible. If I can't compress the fluid, that means its density will remain constant. And those are the three biggies. We have a few more that we'll impose, but basically we have to be viscous effects are neglected, we have to be steady state, and the density has to be constant. Alright, so keep an eye out for this equation. We're going to be using it a lot, and we'll come back to it in the next video to talk about just the slight modification of this that's required to put in the gravity term. All right.